interpretation starts on site. That means that when you're already testing the pile, you need to do some basic actions to make sure that you've collected quality data. It's the rule, the really important rule is just spend a few more minutes on site and don't have to travel there again. So we have to make sure we collected enough information. How much is enough? That depends on your experience. When you're not experienced, collect a lot of information. If you have a tough site, hard conditions, collect a lot of information. Make sure that your traces are consistent. They lie one on top of the other. They are not noise. And look at the amplification on real time, and make sure that you can see the toe reflection, or if it's not possible to see it, make sure that at least the data is quality. All we need to do is on site is to make sure that we have a quality data that can be processed in the office. We don't have to be exact on filtering or sharpening. Amplification should be more or less. Everything should be more or less. We can do that in the office, but we cannot add impacts in the office. All the other parameters are fine and we can change them. So the first thing we're going to look at is the basic interpretation, and we need to know how a bulge or a neck look like, and what's the second reflection of a bulge or a neck. So there is a web application called Pilewave, and here it is. I'm going to switch that to full screen. Wait, before I do that, I'm going to post the link, the URL of this application to the chat window right there. And now I'm going to switch to full screen. Okay, so that's Pilewave. Basically, what we see on top is the reflectogram, just like we see on the PET window. Here we see the shape of the pile, and here we see some kind of a representation of what's going on with the waves. We can draw a pile shape. So this is a simple cylindric pile. We just click Start on top here. So we just click Start, and we can see a pressure wave followed by a tensile wave, and we see the head, the hammer impact, and then the reflection. Now let's say that we have some kind of a necking. We can draw it like that. Okay, and let's hit Start again. What we can see here is that we have the normal hammer impact, and some of it here at this point it splits, and we can see some reflection going up here, and we get a downwards reflection from the necking. And then the rest of the wave continues, and we see the normal end. Okay, so now we know that a necking looks like that. It's in the same direction of the end of the pile. If we look at the pile, the end of the pile is a big necking. So we expect to see any necking in the same direction as the end of the pile. Now what happens when we have a bulge? So let's draw something like that and hit Start. Okay, so when we have a bulge, again, here is the split point. Some of the wave continues downwards, some of it is reflected up. We can see that the reflected wave is also a pressure wave, and we see that this time the reflection points up. Okay, it's important to see that. So bulge points down, sorry, a necking points down, a bulge points up. Now let's look at second reflections. What does that mean? So if we have the necking very shallow, like here, the wave is going to go bounce here back and forth, and we're going to have multiple reflections. So let's just hit start. You know what? Let's start with a simpler case, and that's a necking is simpler. Okay. So we can see first reflection, second reflection, third reflection, fourth reflection, and here we probably see the reflection from the end of the pile. Okay. If we have a bulge, it's a little bit more complicated. I'm gonna, okay. You can see here in PileWave, there's also a library of preset pile shapes. So I've selected a increased profile at the top fourth. So in a bulge, it's a bit more complicated. The first reflection is like we saw before, it's pointing up, but then the second reflection points down, and it alternates up, down, and up, down. You can see up, down, up, down. Now, here, because it's exactly at the quarter, the fourth reflection is exactly on the same location as the reflection from the end of the pile. We just need to know these things. Now, what I want you to see, okay, that's about as much theory as I want to give you on bulges and on neckings. The second thing I want to show you is the effect of friction. So this is a good pile here. If we have a lot of soil friction, which can be because of a high stiff soil or a very high length to diameter ratio, the wave is going to be almost lost. Here we cannot see it at all. We cannot see anything in this area. So we need to apply amplification. And when we amplify, we will be able to see something. So amplification and soil friction go hand in hand. One is actually attenuating the signal, and the amplification amplifies them. And because the attenuation is a logarithmic function, the amplification that we use is an exponential function. If we apply the right amount of amplification, then the amplification is gonna zero the effect of the friction, and we will be able to see the pile as if it's in air. Okay, now everything that I say here is a bit simplified because, as you know, soil profile is not uniform, not always uniform, and sometimes the friction at different layers is different. You have a soft layer, and then at the bottom you have a harder layer, or even rock. Everything changes it, but still, as a principle, that's a rule that you need to understand, that amplification compensates friction. Okay, next subject is what happens when you have a decreased top, a defect very close to the top. So let's look at something like that. Let's even make it a bit more severe. What we can see here is that we get a reflection again and again from this neck. And the exact depth of this neck is going to change the frequency that we're going to see. What we see here is vibrations that are caused because the wave just just attenuates here, or sorry, vibrates here between the top and the defect in a very high frequency. And then we see these sine waves here. So that's important to know, important to see. And we're going to see a real live example of that right now. Okay, where do I go now? Okay, so we understood how a bulge or a leak look like in theory, what's a second reflection, and we also looked at how friction and amplification complete each other, and we saw what is the reflector. Let's go. Okay, I saw here a question from Carlos. What should be the initial position of both friction and amplification to start up with? Okay, so friction, in real life, of course, friction is not something that we can control. The soil creates the friction. It's the soil grab. The higher the SPT end value, or the stiffer the soil, the more friction we have. If we test the pile in air, we have no friction. So we have no control over the friction. It's not a parameter that we can change in PET. We can only change it in the simulation, in the pile wave simulation. Now the amplification, we're gonna follow that in a while in the software, and we have some kind of a amplification calculator, and there are also some kind of initial rules for that. So without any more delay, let's go into the PET software. Okay, so this is the opening screen of the PET software. I hope you all familiar with it, and I'm going to open a sample data project, and I'm just going to open one of the piles. Okay, let's go over all the controls now. The first one is the first one I want to look at is the amplification. When I just move my cursor over the amplification, you can see the gray line there showing me what the amplification is going to look like. Now this pile is 14 meter deep, and if I had no amplification at all, this is how it would look like. We have a clear hammer impact, and then nothing. We definitely need to amplify this signal, and the more we amplify, the clearer we see to reflection. Next to the amplification, there is a magic wand, and if we click the magic wand, it will change the amplification automatically for us, so that the amplitude here is going to be identical to the amplitude here. That's a useful tool. Now, the next thing I'm going to show you here, next to amplification, is the amplification calculator. And for the amplification calculator, you need to enter the wave speed, plane length, diameter of this pile, and the SPT end value. And higher the SPT value, the higher the suggested amplification. The longer the pile, more amplification. The smaller the diameter, more amplification. That's right. Now, you can see here the suggested amplification. When we start going into the hundreds, 200, 300, it means that we are having a hard pile to analyze. If you go over 500, you're going to be lucky to get any results, and beyond that, it's really probably more guesswork than real testing. We just need to know that. So I got suggested amplification 250, and I proved that. I got this value. Okay. Next thing I'm going to look at, I'm going to skip a little bit, and I'm going to go into the wave speed. Wave speed is a critical thing, and we don't really know it. We can calculate it or we can calibrate it, but we don't really know it because the PET is only testing time. We hit the pile and we just wait. The system just waits until there is an echo. It takes a few milliseconds and we get the echo back. The system only records time. So to get actual length, we need to know the wave speed. Now, if we don't know the wave speed, we're going to use 4,000. That's always the center point, the default, the average, and a very good typical value. But if we have some more information, like the concrete age and the concrete grade, then we can get a better guesstimate. Now look, this value that we get here has a lot of scatter. So it really depends on the type of concrete that you get, on the factory, and also that when the factory says it's 30 megapascal, it can be 40, it can be even 45. You never know. So the higher the grade, the higher the wave speed, and also when the concrete ages, the higher wave speed. Now, a wave speed changes by plus minus 10% at most. So 4,400 is the maximum that you're gonna get, and 3,600 is probably the lowest that you're gonna get. So 4,000 is a good starting point. After we tested all piles in the project and we have a reliable reading from a reliable supervisor, not a contractor, we can change the wave speed for all the piles. We're never going to change the wave speed for each pile individually to get the length that we want. This is not testing, this is cheating. So all piles in the project that have been made with the same concrete on the same day should have the same wave speed. It just makes sense. It's the same concrete. The wave speed does not change. More controls. The triangle here is the planned length. And we can change that, either drag it right or left before we start testing, or we can actually type it, 14. Okay. Now, next control I'm going to look at is the end of, let's make it simpler. This control here is the end of the line. Now, when we start testing, the software is going to take about 3 times the planned length. So we can drag here the scale and pull this, and we can see that we have 40-something meters maximum. We cannot drag this more to the right. This is just the amount of information that the software collected. So it's important to set the planned length to approximately the right length. Otherwise, you're not going to get enough information. Now, after we got the planned length correctly, we're going to put this 2 or 3 meters after the planned length, because probably that's where the end is going to be, within this range. Okay, we played with the scale. What we can do here is double click the scale numbers. Can you see anywhere here? I just double click that and it sets the scale for me automatically to about 3 meters beyond the end of line. Next thing is the length mark. The software is going to put the length mark for you automatically at the lowest point. So that's the length mark. But sometimes, I mean, this is an easy case, but sometimes you have a much tougher case to test, and you can move this manually to wherever you think the end is. Okay, so the software just puts it in a very naive location, just the lowest point of the curve, which is here. It's up to you to look at it and see that it makes sense, to apply your judgment, which we're going to talk about in a while. Okay, so we covered the length mark, planned length, end of line.
There are 2 questions.
Okay, and okay, let's answer a few questions here.
Look at the last two questions.
Okay, so Fernanda asked how much longer should the curve be after the last peak? So typically 2, 3, 4 meters, something like that. We don't want to put it here because we're actually going to miss the peak. So we're going to put it a few more meters after it. Now, the other important of the end of line is this is the location that gets the maximum amplification. I can draw here the amplification curve, this curve here. This shows where the amplification goes. And you can see that in this location, we get maximum amplification. It's important to know that. If we drag this more, we get less amplification in other locations, maximum amplification here. Okay. Okay, another question was when the wave crosses the x-axis here, what does that mean? The answer is nothing. Okay, you can see that if I change the amplification, the wave goes a little bit up or down, above and below the graph here. So this point here can change a little bit above and below. The software shifts and rotates the curve, and the actual location above or below the x-axis has zero meaning. What we are looking for is big changes like this or that, or something in the middle, which we don't have here. As I told you before, this is a good pile, and I'm just gonna look at it just to teach you the control. Next thing that we are gonna look at is the filter. The filter, as you can see here, we have a little bit of rugged data here. The filter just irons it out. Why do we need that? Because when we make the report, we want to make it presentable. We want to actually control the amount of questions that we're gonna get. We want to show the information, the important information clearly, and not to show really silly little things like all these little things. So if someone is going to ask me, why do I have this little bulge here? It's really a silly question. It's much easier if we filter that out so that we can get a presentable information that focuses on the important features. Now, having said that, we don't want to abuse the filter and the sharpening and to hide everything. Okay, we can make everything look too good. We don't want to do that. We want to use the minimum amount of filtering and sharpening to make the data presentable and to focus on the important features. Okay, let me just for a second see if we forgot something. We went over scale, wave speed, end of line, length mark, amplification, filter sharp. Okay, so we still need to look at the impacts node, impact list, and the nodes. Two important points. Okay, impact list is here. What we see here, the blue line is actually the average of all the impacts, and we have here at 10 impacts, which you can see here. So each of the impacts is shown in a gray line beyond the average. You can see that they are quite one on top of the other, which is nice, which means that we have a very repeatable information. If we will stretch the line and we will look far beyond that, we can see that the waves already start to diverge, and we are just amplifying a lot of noise here, which we don't want. Okay, so we have all the impacts, and here we can see them in the impact list. We can either click here on an impact and see it on the impact list, or click on it here. What else can we do with the impact list? We can we can select an impact, for example, this one, and then I can sort by clicking the sort icon, I can sort the impacts by similarity. So the impacts on top are going to be the least similar impacts. You can see that the one here is least similar, and the ones on the bottom are going to be the most similar. I can select a few, and I can see the selected ones. Let's say I selected just a few impacts, and then what I can do is I can hide the other ones. I can just select delete others, and I'm left with just a few impacts. I can just a little bit fine-tune that by selecting again impact, pressing delete. Now I have 4 identical impacts, which is a nice set. Now, why do we delete impacts? We don't really delete them. They are just going into a recycle bin, which is saved with the pile, and it's always there, and I can always undelete them all. So I've undeleted all, I got them all back. I just hide them actually. The reason for hiding impacts is that sometimes we hit a broken piece of concrete, a bad location in the pile, a loose piece of gravel, or just the reinforcement bars. And then we get some noisy data that we want to just hide because it's irrelevant. But we want to make sure that we have a good set of impacts to start working with. So the bare minimum, the really bare minimum is 3 consistent impacts. You don't have 3 consistent impacts, don't do any interpretation. You have to go and do testing again. And that's why I told you collect enough information on site. And when you don't have enough experience, collect 50 impacts. Look that they are consistent so that you will have enough impacts to work with later on in the office. Okay, the next thing I want to show you is the notes. Okay, the notes is just something that you can write. Okay, I can write here good pile. Typically we don't write good pile, we just leave it empty. Okay, let's say we have a problem in this pile, so I can write problem at 5 meters. But it's much easier, instead of writing problem at 5 meters, is just to take my cursor and click it exactly where I want. So here or here. So it's just selecting it for me. Okay, now let's say I have a lot of piles with a similar note that I want to say. I can use the hash sign here, like that, and then I click the plus icon to save it. Okay, now I have here a list of nodes. I just select the one that I want, click on the length that I want, and I got it. I don't have to retype it. Okay, if I don't like this anymore, this comment, I can just select it and remove it, and it's out of the list. So this is a little labor-saving feature, so you don't have to type again and again and again the same comments. Okay, so now we know the controls.
Can you look at the last 4 questions?
Okay, Jorge asked if it's possible to get different results by doing the same test on 2 different days. When the pile is very fresh, you are going to get different results every day because the concrete changes. We're testing a live, fresh concrete, and every day it's going to react differently and the wave speed is going to be increased. So we're expecting to get a higher wave speed, or if we set the same wave speed, we're going to get it's going to look longer every day, just because the waves are going to be faster and faster. But typically, same pile, same results. Doesn't matter if you test it in different days or different testers or even different systems. Same pile, same results. I mean, otherwise, what are we doing here? Okay. Now, if we hit different locations on the piles, the results are going to vary slightly, but nothing significant is going to change. Let's go back to our presentation to make sure I did not forget anything. Okay, we covered that. Let's go to the next one. Okay, now I'm going to give you a recipe for doing the interpretation of a pile. So the first thing that I want to check consistency and hide abnormal impacts. I'm going to add to that that we also need to check that we have enough information. Then we're going to check the wave speed, set the amplification, and the end of file. So let's not follow all this now. We're going to go back into that. Okay, so let's say I got this pile like that from the field. So first thing I want to see is that I've got consistent information. And here I can see that some of the impacts are a little bit off. I can hide them for now. That's insignificant. Okay. The second thing I'm going to look at is the amplification. And this amplification is definitely too small for a pile that long. So I'm going to increase it until I start seeing something. Yeah. So that makes sense. And I can also click here the magic wand, set amplification automatically. Okay. I'm going to put the length cursor exactly where I need it. Perfect. Now, the wave speed is something that we usually put on site already when we start testing, but we need to look at it and make sure that we got it correctly. So let's say 4,000 makes sense in this case. And we go back to our recipe. So we got consistency. Oh, sorry. Okay. So we got the consistency, the wave speed, amplification, and offline is very important. And we're going to go and do this recipe again and again in harder piles, in different conditions, and then we're going to go into a more advanced controls. So the end of line is this point here, and it has a significant effect on the pile because, as I told you, this is where the amplification is maximum. So here we don't see a lot of effect, but in future piles, when I'll show you, it's going to get a much more significant effect. Okay, next thing is I'm just going to set the filtering and the sharp to something nice just to be presentable. I typically don't want to go over sharp 2 for a presentation. I can do that for analysis, and we'll show that soon, but not for the presentation. Okay, and we have no comments for this pile whatsoever, so we can save it and go to the next piles. Okay, back to our recipe. Reselect impacts. We're going to go there and do that on a harder to interpret pile, and let's write notes. Something important that I wrote here, which is really the difference between a cowboy and a tester, is using the question mark sign, and let me show you that now. So let's say we have a pile here, and we really don't know what's going on here. We can see that we have inconsistent results. We cannot trust this data here. What we're going to do here, we're going to click here, and this control here, and it's going to show us that we really don't know. Okay, that's how it's going to look in your report. I wrote here the name of the pile is luck, because although it looks like a very nice pile, when we look at the actual impacts, we only have 8 impacts here. Each one is really different. And it just happened to be good luck that the average looks like a pile, but it's really a garbage data. And this pile is not something that we can work with. Let's take another case here. Okay, so this pile is planned to be 12 something meters, but at 12 meter we don't see anything really that makes sense. We get something here at 9.2 meters, but that can be a second reflection. We don't really know if that's really the end of the pile or noise. Let's say we're not really sure. What we're gonna do is we're just gonna add a question mark here to the pile. So remember QM1, that's how it's gonna look in your report. And it's okay, actually it's more than okay to use question marks sometimes, because some projects are hard to test. I mean, we are not always lucky to get very short piles in very soft soils where the system performs perfectly. We're going to be asked to do testing in projects that are marginally or beyond marginally good for this method, and I know that we have to test them. So in these cases, we need to use a lot of question marks. The piles might be too long, or the soil might be too stiff, and we simply don't know. The method has limitations, and we should know them, and we should show the engineers or the guys who are ordering the report that we are uncertain, and that the test just could not tell you what the length of the pile is in this case. An important point here. Typically, all piles or most piles in the projects, or at least the groups of piles, are similar. They have the same length, they look the same. And let's say we have a villa with 30 piles. They all look great. One of them looks different. Even if we don't know exactly what the problem is with this pile, we know that it's abnormal. It's separating the good from the bad piles. So there's a lot of power in looking at the whole project, zooming out, seeing all our piles, and then zooming back in. And that's really a powerful feature of this method. So sometimes it's really impossible to know what's going on if we test just one pile. But when we test all the project, we already get the feel of how a typical pile in this project looks like, and we can see the abnormals. So what I'm going to show you now is 3 features that are related to zooming out and then zooming in again. Okay, so I have here a project. You know what? Let's make a little break. I'm going to show this little feature here. This is a map of this pile. These piles were tested with the Bluetooth pad, and we can see the location of these piles. We can even, because it's a satellite, it's a Google Maps, we can even see a satellite photo, and we can even take this little man here, and he shows us exactly where the piles are going to be. So of course, the GPS location is the location of the phone or the Android device, and it's accurate to 2 or 3 meters, but still it's cool. And if we click on one of the piles, it's immediately opening it. So I just wanted to brag on this nice little feature. It has nothing to do with interpretation. Okay, what we see here is the list of the piles, and we can see that most of them are quite similar. We can see here the icons here that we see. This one means that we have a GPS location, and this one means that we have a photo of this pile taken. So the tester took a photo of each of the piles. Again, this is nothing to do with interpretation. He just wanted to show that he was there, and later on, if there are any questions, he want to show us what's going on. So because all these piles are similar, we can, let's first, okay, these piles are similar. So they all should have approximately the same parameters. So I'm going to look at one of the piles that has a good parameter. I'm going to analyze it a little bit. Okay, I'm going to add some filtering and sharpening. Okay, let's say that I like it. Okay, so I got amplification 70, filters 10, and sharpening 2. I'm going to save it, and then I'm going to go here in our menu to File, Modify All. And in the Modify All, I'm going to set the length scale for everyone to the same. The wave speed is going to be 4,000 for all piles here. Amplification, filter, sharpness, all going to be the same. And I changed all the piles to use exactly the same parameters in a bulk. That's useful. So now we can look at them and we can compare them. It does not mean that we cannot change individual parameters later on. For example, in this pile, 70 is a bit too much and we need to use much less amplification. That's fine. Still, we get a good starting point. Okay, so now because all these piles are similar, I'm gonna have a feature here in the tools menu. Calculate and add average pile. I'm gonna do that. And a new pile was created for me. And this pile, the name is gonna be average. And it's an average of all piles. Let's look at this pile. So what we see here, each of these impacts is actually one different pile. The average of a different pile. What? Pardon?
Something went.
Can you still see me?
Maybe I was turned off. Okay.
Okay, we might have a technical problem. If you cannot see me, please raise your hand.
No, it's everything okay. It's just me.
Okay, okay. False alarm. Nothing happened. So we have here the average pile, which looks like a very nice pile. Okay, we're gonna save that. What's the added value of the average pile? Let's look at one of the other piles. For example, I'm gonna look here and I'm gonna find a suspicious one. I don't know. Let's say this one. Okay, so something here looks different from the other piles. How can I tell? I have here the compare button. Now the compare button lets me compare this pile to any other pile. So I can see that comparing this pile to pile number 2, it's a bit longer and generally okay. I can also compare it to the average pile. And now I can see that this pile might be a bit longer and that this feature here that I see on this pile compared to the average pile is no big deal. Okay, it really helps when you have a uniform soil layer change and all piles are showing you a typical feature in the curve in the same location. Let's say a bulge that looks in the same location. Now, because the soil layer is approximately in the same depth, we're gonna see that in the average, and then when we compare, we can see that maybe this pile is really abnormal compared to the average or the typical pile, and we can still look at it and analyze the defect. Okay. Let's go back to this example here. So let's go back to our recipe here. Okay, so I've taken one of these piles, which is not such a nice example here. And what we can see here is that we have really a sine wave here, almost a reflector, almost like a perfect sine wave. How can we analyze that? So we have two methods. One of the first method is the FFT button here. We look at the FFT. FFT is actually showing you the pile in frequency domain instead of time domain. But because we have the wave speed, each frequency, for example, 1 kilohertz is 1 millisecond. And 1 millisecond, if we know that the wave speed is 4,000 per second, is 4 meters up and down, is 2 meters. So 1 kilohertz is going to be exactly presented in 2 meters scale. So because of that, we can convert everything to depth scale or length scale, and which makes it much easier to interpret. So now when we look here at the FFT curve, we see a very sharp peak here. And we can tell that we have a reflector at this depth, 1.8 meters. Now, this is a very typical length for a temporary casing. And this is a phenomenon that happens a lot when we have temporary casing. And when the casing is pulled out, naturally, we have a step in the pile, a change of diameters. And because of that, we can see that reflector here. So FFT is one of our methods to do that. The other one is the repetition marks, this icon here. And when we click the repetition marks, we can see as 10 markers, and we can change them together. So they're going to keep equal distance. If we change them here, and we can try to put them one on top of the other, and yep, we can see that they're all overlapping the peaks in the pile. Okay. So we can tell that this is the first one is the length of the reflector. And again, we can type reflector at, and we just look at this one here, and we got it. Okay, so two identical methods, different approaches to the same thing, either the FFT or the reflector method, the repetition marks method is basically two methods for showing you the same thing. The repetition marks is a little bit more intuitive, and the FFT takes a little time to get used to, but they're basically the same thing. So hiding FFT, hiding that. This is what we saw in the reflector, and this is again what we saw here in the when we had the in pile wave. When we had something like that, we can see a very similar thing, a reflector.
There's a question about the previous example before you move on.
The previous example, this one here.
Look at the question on the notes.
Yeah, from in the previous example, we indicate an increase in the shaft in the section where the curve occur widened above. I think you mean can't really find it now. Where was it? I think it was in this site. Sorry. This one.
Yes,
Is that
this
the one? Yeah. Okay. So this, the question is if this indicates an increased cross section in the point of the pile. Well, theoretically, yes. But if you look at this, it's really minor, and you should just ignore it. Okay. We're looking for bigger features, things like that. Okay. That's a typical feature of the pile. Interpreting that would probably, in most cases, be over-interpretation. We're going to look at this in a while. Okay, we can try to put this into signal matching and see that it's not really going to give us anything dramatic in this area. So let's continue with our presentation. We've done reflectors and FFT. Next thing is signal matching. Now, a word of warning. Signal matching is and always will be an experimental feature. You should never use it as a silver bullet, as your medicine, the panacea that will cure everything, and it should never replace your good engineering judgment. Your engineering judgment is the most valuable tool, and no automatic interpretation, no AI, and no magic is going to replace your good engineering judgment. Having said that, let's go and do the magic. Okay, so signal matching is here. And when we click that, we can see the signal matching window. Now, signal matching can be done manually. I can change here the amount of friction. I can also, if I have different layers, I can change the friction profile, which I normally don't do. I just right-click a point to delete it, or just create a point and drag it. Okay, so I have here the friction profile, and I first want to see that I have the approximate match. Okay, what we see here, the blue line is the measured pile, and the orange line is the simulated one. Now, I can change, just like I did in PileWave, I can change the profile of the pile, and I can see the effects. And the idea is to change the profile to get a good approximation of the pile. So if we want to see what happens in this area, we can try to emulate a little bit increased cross section, maybe something like that. Okay, something like that. So not a huge difference. And the nice thing is that we can also click here the match button here. I click the match button, and it's going to try to do it for me automatically. So the software is now trying a lot of variations. You can see here that it's really testing a lot of variations like crazy. It's actually a genetic algorithm, or that tries a lot of changes and mutations until it improves the solution. And you can see here the match quality. So the match quality will always increase. And you can see that there is really a very little change here in the profile. Really nothing to write in your comments about. So it's really a very small, insignificant change here that caused this area here to show. And what we can see here, that we already have a very nice match. Everything matches really nicely. 81 is a nice match, so we can just stop it manually. And then we can either save this match, so we don't have to do it again, or we can actually even generate a report of that. So we got a report showing us the profile of the pile in percentage, etc. Nothing really to write home about. I hope this answers your question, Jorge. Okay. So that was a signal matching. Now let's try to do signal matching in a more challenging pile. Sorry. Okay, so that's a more challenging example. As we remember from the theory, when we have a necking, it goes down, and then when we have a bulge, it goes up. So this means that we had a necking that ended here, a temporary necking. Let's show you what it means. Okay, so this is a local necking, and as you can see, the local necking goes down and then up because it goes in and then out. So it's like a necking followed by a bulge. Okay, fine. Let's go and back to the software and see how this looks in signal matching. I mean, you don't have to. I mean, you could write just here, select from the nodes and say necking at here, and you'll be fine. But if you want to really get some assistance or to get more confidence in your analysis, let's go and do the signal matching. So first I'm going to do something like that. And you can already see that a simple manual change, I can, really fine tune it here, but it's really not that important. A local necking here caused this thing here. Very easy to see, and we can just save it and report it. Okay. I really suggest that you will try to do the matching manually as much as possible, just to get the practice and to get actually the feeling and the theory of what you're expecting to get. Because it's very tempting to just press the match button and let it do the magic for you, but it's not going to make you a better tester. Okay. You're going to get approximately the same thing. By the way, there are many solutions to the same problem, and you can get different issues, different solutions that will look exactly the same. So that's also a good solution here. A little necking here after a small increase. They both look quite good, and you can go with both answers, but I would always say this is a necking here followed by a bulge. Now this here could be the second reflection from the same neck, and if we'll take the repetition markers, we can see that they are quite they match quite nicely. So that's the first reflection, second reflection, and we don't see any more. And probably because this is already in 5 meters, we're not going to see much in the FFT. The FFT is only good for 2 to 3 meters. After that, not much. We can also try to stretch it a little bit and then do the FFT. So we get a little bit of bulge here, which just confirms our thought, but we are really amplifying noise in this area, and it's meaningless. And A very nice thing that was added to the recent software version is the undo button here. So I don't have to think what I just messed with the pile. I just do a few undo clicks and I'm good. I've done everything. Okay. So let's get back here. Yeah, that's about concludes our meeting for today, and we're also just on time. It's 8 o'clock. So I'm gonna take your answers for the next few minutes. Sorry, I'm gonna take your questions, and I can see another question. By Jorge. When a repetitive wave is generated by a widening in the pile head, for example, how do I identify if a shaft widening appears in a greater depth because both signals are mixed? Yeah, that's a great question. But I'm afraid I don't really have good news. When you have a top defect in the pile or one defect, it's very hard to see anything below that. I showed you that in pile wave, and you can see that in many examples. Usually, if you have one defect, you're lucky to see anything below that because the repeating waves are just mixed, and the best that you can do is sometimes see the end of the pile, sometimes you don't see anything at all. The problem is to trying to do over interpretation in these cases. Let's see if I've got a. Yeah, I wanted also to show you a project that I got today. I got this today from a customer. The piles are all supposed to be 24 meters long, and they are horrible. The piles are only 45 centimeters in diameter, but 24 meters long. So that's 50 something diameters. The SPT profile shows that we have a varying SPT from starting from 10 to 50. So that's a very stiff soil at the bottom, and 50 diameters with a very high FFT, with very high SPT values means that you're not going to get much. However, in some piles, we can see that we have here, let's try to clear a little bit all the mess here. Okay. So in some piles, we can see some reflection here, which could be made a little bit more representative if we apply more sharpening and more filtering. But in these cases, what you must do is write in your report that these piles are beyond the limitation of this method. So a question mark was added here because this could be just luck or noise or I don't know really what. And the signals are matched here. But if you look here, we have a huge feature on top, and that's probably the feature that is generating maybe all the reflections in this pile. We don't know. So these piles are definitely beyond the limitation of this method. And if you're trying to test a pile with 50 diameters, you're not going to get much. Again, look here. In this case, this pile definitely has a huge bulge in this area. Remember, it's going first up, then down. So it's a local bulge. And after that, this might be the second reflection. Who knows? No, so trying really analyzing these piles is very risky because you're just going to write nonsense. Okay, you can give information about the first 10, 15 meters, but everything that happens in this area of the pile is just voodoo. We don't really know. The signal is lost. We need a huge amount of amplification, and so we're already amplifying noise, and you can already see that signals are starting to diverge in this area. Again, you can see the signals are really matching nicely up to about this depth. After that, nothing. Still, the information that you get from the first top 10 to 15 meters is valuable, and you can use it. Look at that. What a mess. I don't even want to start interpreting this pile. I mean, it's almost impossible in this case. It's probably defective and beyond the limitation of this method, and too slender, and the soil is too stiff. So forget it. I'm not going to do interpretation on these piles. I'm just going to say in my report, sorry, these piles are beyond the limitations of this method. A question from Fernanda. Can we have different wave speeds in the same project, Fernanda? If the piles were made in different days, not day after day, but let's say they have a few weeks between them, then yes, definitely. But we have to make sure that we set the same wave speed to all the piles that were made in the same day by the same concrete. It's just a feature of the concretes. And the worst thing that you can do is to change the wave speed for each pile to set the correct wave. So what I'm going to show you now is a big no-no. Let's say I want to make the contractor happy. I'm going to make this 24 meter, and then the next pile I'm going to make the length mark here, and maybe it's too much, so I'm going to put it here, and I'm changing the wave speed for each of these piles to make everyone happy. This is wrong. This is not testing. This is really cheating. And if you see a project that each pile has a different wave speed, 4,000, 4,300, then you know that someone is not really a pile tester. He's just a pleaser, trying to please the contractor or whoever. All these piles that were made on the same day with the same concrete must have the same wave speed. I'm going to go here to pile, modify all, and give them all the same wave speed according to my best knowledge or to the calculator. So 4,100. Okay. More questions, please. Okay, I want to remind you that you can post more questions to support at Piletest.com. That's
You can also ask now in Spanish, and we'll have them translated and back for the answer as well.
Yeah. You can write here in the chat window your questions in Spanish. So I'm going to give this another half a minute, and if not, then thank you very much. Got in mute. Mute, please.
Me.
Yourself. Because there's an echo. Okay. I can see. Israel. So I didn't. I'm sorry, I missed your question. Izar, I hope I pronounced your name correctly. What is the physical meaning of impact, and how to decide which impact would be respective pile under consideration? Okay, so let me go back to the software. we never analyze based on one impact trace. We hit the pile many times, and what we want to see is that the impact traces are consistent. Because if we hit a broken piece of pile, then each impact is going to look exactly, each impact is going to look different. Like, where was it? I had a good example for that. Yeah. Okay. What we can see here is that the average looks great. I called this pile luck. But each impact trace is different. This pile was really just hit, I don't know, by on a broken piece of concrete or on the reinforcement bar. We don't see any consistency. So this is definitely not quality data. In fact, this is garbage data. And because of that, we do not analyze that. We do not see anything representative. But if we look at this pile, we can see that all the impact traces are more or less the same. I mean, we're still using the hammer with our hand. It's not a mechanical hammer that delivers exactly the same impact. And also the pile changes a little bit. We break a little piece of gravel, but still all the impacts are one on top of the other. Here, again, one on top of the other, more or less. So we don't need a representative impact trace. We look at all the cloud of the impacts. Here we have 11 impacts. Here we have 20 impacts, and we can hardly see that they are different. Okay, they are really one on top of the other. We can only see that they are separating if we look farther up the pile, and even there, no, sorry, they're just one on top of the other. So here in this case, we have a very consistent result. And because of that, we know that this is not random noise data. This is data that we can trust. It's a real data coming from actually from the depths of the pile, and not just some kind of a random noise that came from hitting the reinforcement bars or a broken piece of concrete. Because when we hit a broken piece of concrete, each impact is going to look different. It's impossible to get them exactly the same. But when we hit the real pile, then we get consistent data, like in this case, 20 identical impacts, when we know that we can trust them and we know that we can analyze them. So I hope this answers your question as well. Okay. Fernanda, how can I know if the final peak is up or down? Okay, and let's go back to pile wave. And in a normal pile, the reflection is going to be in the same direction as the hammer impact. We can reverse that because some users are used to the notation where the signal goes up first, but it's just a matter of getting used to it. We are really used to seeing the initial velocity curve pointing down. It's downwards velocity pointing down. So this is the actual hammer impact going down. Now, if we had a pile which is anchored in rock, for example, something like that, let's say this is like an infinite space here. So it's actually a concrete pile, and after that, a rock bottom. We're going to have the reflection pointing up, because the pile is really connected well to the rock. It's rock socketed, and therefore the rock behaves like a big bulge or increased cross section of the pile. So this is what we get here. So again, a free-end pile is going to look down, and a rock socketed pile is going to look upwards. Now, it's it's not binary, it's not black and white, because sometimes the rock socket is just a harder soil, and you can get, in some cases, debt or a very small one or anything. And sometimes in ideal conditions, you can have really a neutral, no response, because all the wave is just going to disappear into the soil at the end, and we're going to get no reflection. So everything is possible. But again, free end pointing up, free end pointing down, rock socketed pile pointing up, and everything in between can happen. Oh, I see another question from Jorge, and thank you for translating it to English for me. Where there is a decrease in the pile in depth, is the peak of the wave inverse to the whitening? Okay, all these questions you can really check with a pile wave. Let's say if we have a decrease of the pile in depth, something like that, you're going to have a reflection just like any other reflection, just like any other necking in the pile. And the peak is going to be exactly the same as the end of the pile. And next question from Radip. It's hard to find bottom reflection in gravel. Well, there are two reasons why it's hard to find a reflection in gravel. And again, I'm going to simulate it. So the first thing is I'm going to give you the profile of a pile in gravel. It's going to look something like that. Okay, very jagged. The second thing is that gravel has a very good grab, a very high friction. So it's going to look like that. And then when you combine the two, you're going to get a very noisy signal. And if we get more friction, you're going to have to use more amplification. And the more amplification you use, you also amplify all these little noises here. Now, if this was just mild, okay, if we use a more random pile shape, which you can get in gravel, okay, it's going to look something like that. So it's quite hard to identify this as the end of the pile because we got a lot of noise here. And if we really go to the extreme case, and it's not that extreme in gravel, okay, the shape of the pile looks like that. Now, it's not very good for testing, but it's very good for construction. This pile gives an excellent soil friction or good soil grab. So it has a good resistance. And when we test this pile, you're going to be very brave to declare this is the end of the pile. Okay, or really, so it doesn't really matter then how much you amplify. The signal is just going to get lost. First, because it's going to be amplified, it's going to be reflected from all these things here. And second, because gravel gives you a lot of friction. So that's why it's hard to find bottom reflection in gravel. Hope that answers your questions. Oh, I got more questions here. It's an amplification, changing factor, dependence. Okay, how do we actually get the amplification? I'm going to post here another page. I'm going to put it in the chat window, the URL. And that's pile calculators. Now, this is going to give us the attenuation of the pile, which is also the amplification. So let's say we have a typical wave speed. The pile length is going to be 25 meters, and the diameter is going to be 70 centimeters. And SPT is going to be 10. So we need all these factors: wave speed, length, diameter, and SPT. And when we have these parameters, we can tell what amplification we're going to need. Now, if the SPT increases just a little bit, it has a dramatic effect on the amplification. And if we have here SPT of 20, we're already getting a very high attenuation, and attenuation just matches the amplification needed. There's a little formula here, and also a link to a paper and that explains that, the role of amplification on low strength signal testing. But the link that I posted in the chat window is going to show you everything. Here you see the relations between length to diameter, amplification, and SPT values. Very short article, very easy to read. In general, this area is the easy to test area. This is medium. And this area here with amplifications above 300-400 is the dead zone. It's really hard to test piles like that. So if we have this case here, 25 meters, 70 centimeters diameter, and SPT 20, it's going to be a very hard pile to test. Let me take just one last questions because we are running out of time. And I'm going to answer your questions later on. I would really prefer it if you can send them to by mail to support, and then I can really take my time and answer each one of them individually. Fernando, do we have similar reflection in sand? Yes, sand is a good uniform soil, and we get a standard reflection, just like we saw in pile wave. Is it possible to use the equipment in micropiles? The short answer is no, and let me show you why. Let's say I have a 10-meter micropile, but the diameter is just 10 centimeters. You're gonna get an amplifications of 1,000. Okay, L to D ratio in micropiles is typically too high to allow any testing, even if the N value is low. Okay, even if we have a very low N value. So short answer is no. This method is not good for micropiles. Can I have a pile design notes kind of calculations spreadsheet that you can? Israr, yeah, I think the link that I sent above should help you with the stability of the pile. Okay, Piletest does not give any advices about pile design. That's out of our scope. We do pile testing systems, and we can help you with the analysis. Okay, everyone, thank you very much. This has been a pleasure hosting you, and I really hope that we will do more webinars like that. The best way would be if you can really send us more questions, and then we can do another focus webinar answering your focus questions. Thank you very much, and hope to see you again.